Good afternoon, delegates and fellow speakers. I would like to start by thanking ETAuto for getting us all together here, of course, virtually, and for the opportunity for Gamma Technologies to contribute at this congregation of product development experts. In my talk, I would like to put forward a couple of new concepts, namely computer aided strategy, CAS, and smarter testing using virtual approaches, and how this can help company like yours to de-risk your product development strategy. So let's get started by first understanding what are the key technology challenges out there today. We've seen lawsuits faced by OEMs, which are because they could not meet safety standards, warranty, or emission regulations with causes like battery fire, range loss early in the product cycle, use cycle, and also scandals like Dieselgate. And these in turn obviously result in a loss of company's reputation. And in turn, that results in market share loss, which is very dear to any company and can take decades, if not years, to come, to regain the trust of the customers. Now, the question is, how do we de-risk such failures early on? And the answer, according to me, lies in system level understanding in the real world conditions. Designing and optimizing systems only at a component level is not sufficient anymore. So I want to highlight in my talk today some practical and proven ideas which have helped people answer some of these challenging questions. Before I get started, let me introduce our company, Gamma Technologies, and our product, GT Suite. We're an innovator in the field of system simulations and have been focused in this area for the last 25 years. We are spread across the globe and cater to the global clients. GT Suite is a multi-physics simulation platform, a truly single interface with a single solver for all systems and all physics. Since the start, we've been focused on leading the way for system modeling with our customer-centric development and support initiatives, which is evident with the kind words that a lot of the clients have to say for us. Now, let's talk a little bit about GT Suite's DNA. So GT Suite is unique in the offering where you can focus your early studies of doing system level analysis like vehicle architecture studies, early stage concepts, and also at the same time within the same platform, go to detailed component level analysis using 1D, 3D seamless integration, which can then be all brought together to do a vehicle level virtualization, which has all your components in fair amount of details as well as the system. And all of this can be used to understand, as I said earlier, the system level transients with real world environments, which as discussed is the need of the hour. In summary, GT Suite is aligned with the philosophy of a digital twin, living throughout the development cycle of your product and maturing with it from the early design stages to controls and development such as Sill Hill in the Sill Hill environments. Now let's zoom back and focus on the question we asked ourselves earlier. The automotive industry today is going through a drastic change. People have to place bets on their strategy and their outlook for the next 5 to 10 years. How is the company perception? How is the company outlook with respect to technology is going to look like? And these strategies are dependent on various factors, such as policy, technology fit, as well as most importantly, customer fit. And all OEMs today are looking at the holistic picture and trying to create a strategy, a product strategy that makes them successful today, but also de-risk their strategy for the next decade to come. So the question is, how do we take these new concepts and de-risk the strategy very early on? So here I would like to introduce my first concept. I call it computer-aided strategy. In engineering, we have today heard words like CAD, that's computer-aided design, computer-aided engineering, CAE. However, simulations can not only help you move to the left in your V cycle, but I propose that we can actually use system-level models with real-world environments to actually help you analyze at the strategy phase as well. Now, typically, the strategy phase involves market research, taking existing technologies and trying to identify what technology works best for your company. So that can be, the simulations can be used a lot there as well to analyze the systems in real environments. And let's now, switch gears and talk about some real life examples of some leading OEMs who have deployed such technology to answer very difficult questions. So the first question I want to talk about is, how can a company design an EV skid? So that's basically just a common platform of the electric vehicle which can then be fitted to various platforms. It's a complicated question. We have to study a lot of trade-offs. But here's a quick example how the advanced engineering team created a detailed yet accurate electric vehicle model with an automated builder very quickly called GT Drive Plus. And then on top of that, they applied design of experiments to analyze the entire design space within days, not even a week, less than a week. And at the end, they could look at the Pareto front of optimal designs and select the 40, which is in the dark blue on the top right, that work for them and give us the best global trade-offs. Let's also look at some more general and higher level questions. What is the best vehicle specification for a given market? An OEM might ask in their strategy phase. What is the best powertrain to meet this specification? Now, here's an example of a process that Bosch has developed around GT Suite, where they can put into the mix the vehicle powertrain topology, powertrain configuration, operating strategies, and throw at it any duty cycle and identify which of these results in the minimum CO2 for the given duty cycle. Now, there are many design options here for a given duty cycle, and they actually do tens and thousands of simulations to find out what is the most optimal design using parallelization and reduce the time it takes to do such studies by 85%. And in the end, they can actually evaluate the entire design space for their customers. It's an innovative approach that shortens their decision timeline and makes them very confident about their decisions. Now, we've talked about simulation techniques that can help you analyze your systems at a very early stage right now with tools like GT Drive Plus. Let's also discuss, okay, we've got a great model. We've got everything that works for us, but how do we give realistic real world conditions and put the chaos of the real world, be it traffic, be it elevation, be it traffic lights. These are all things that are very dynamic in nature. How do we go ahead and put that into our simulation models so that we can accurately take the real world boundary conditions into our models as well? And that is possible with GT Real Drive. So GT Real, what we have done here is we've taken the ability to have Google Map-like features, point anywhere in the world from A to B, and select your route options. Do you want to drive on a highway? And then you actually come up with a drive profile that will have the elevation data, traffic data, and then you can run your virtual model any place in the world and validate how it's going to perform with respect to range, emissions, etc. Now that we've given a few industrial examples for computer-aided strategy, let's talk about the second idea that I have. That's about smarter testing. In the distinguished audience today, we have many who are experts on testing and testing automation. With automation, we've made our testing smart. So we call it smart testing. However, I want to introduce the concept of smarter testing, where we can symbiotically use virtual and physical testing approaches to reduce the burden on physical testing. As we know, vehicle development times have reduced drastically. They've come down, as Volvo says in this paper, by 50%. They've been reduced to half over the last decade. Now, there are many systems that are not possible to be tested physically and comprehensively in this short duration, where if you want to be competitive, you have to launch your vehicles in the short period of time. For example, electric vehicles, batteries. Now, batteries age, as we all know, but how do we make sure that we test the aging profile of the battery? Now, the battery might age over 1 year, over 2 years, 3 years. That's a very long time to run your tests. A similar opportunity exists in conventional powertrains as well. Engine calibration is getting more and more demanding because of the multiple knobs that you can use to run your engine the best way possible. And the testing for that to develop a calibration can take up to 2 to 6 months. And we don't have that kind of time with the product development timelines that we have today. So I want to discuss how can we use smarter testing in such approaches. The first example that I have here is for cell qualification. Everyone in the EV space knows that you have to procure cell if you're a pack manufacturer or if you're an OEM, and you have to make sure that it runs the life cycle that the vendor is mentioning that it would. And what if those cells might run, but your pack design might not allow them to operate at their full potential? So there's a lot of unknowns. So the first example here is we have actually testing data for about 870 days of cell aging. And on the top left, to develop an electrochemical model that can predict the aging, we've used all of that data. We've used 870 days worth of data to build that model. But at the bottom right, you will see we've only used 50 days worth of that data. And yet the model was able to predict the aging characteristics of that cell pretty accurately. So you can imagine the potential here. You can reduce 3 years of testing to 50 days of physical testing and replace the rest with virtual testing. And that's going to save you a lot of time and accelerate your product development. Now, once you have your aging models of your cell, you can actually put them in a system model, be it a vehicle, be it a ship, be it an aeroplane, and deploy on that the real world conditions that we've been emphasizing on throughout this talk. So that would be commuting behavior, weather patterns, and charging patterns. And that will give you more meaningful predictions on your real life usage. So here's a quick example of what the output of such a study would look like. So if it's a car running for weeks and weeks, and here we are going through 400 cycles, and each cycle represents a week. So it's about 8 years where the car is running through a work week, through a weekend, through different weather patterns, through different charging patterns. And at the end, you're looking at how the battery is degrading. And you see that, and this model actually ran in 6 hours. So you're running 8 years worth of testing in 6 hours. That's 11,000 times faster than real time. And this would be very interesting to OEMs and pack suppliers, because here you can put all your variables, temperature, use profile, charging profile, etc., and define what's the worst case for your battery, so that you can give the right warranty. As you know, if you give too lenient a warranty, you're risking yourself to recalls. And if you're too strict with your warranty estimates, then you are not being competitive enough in the market. After these cell analysis done, you can actually integrate the cell models with the entire thermal circuit and the electrical circuit, and then predict risk failures like thermal runaway. So here I have a cylindrical cell pack, which one of the corner cells actually goes into thermal runaway, and we are checking if the whole pack goes into thermal runaway. And this model is predicting, yes, the whole pack will actually catch fire. This is a very interesting thing that you can study virtually. And actually, there was a detailed study and validation done by NASA, and you can find details of the paper here at the link below. Now, switching gears, we've talked about smarter testing for electric vehicles, for battery packs. Let's look at another example in conventional vehicles, as I mentioned. Now, for doing engine-based calibration, right, you typically would run the engine on a dyno for about 10,000 to 60,000 points, which might take 3 to 8 months. And then that data is given to your ECU supplier, or you might have internal calibration teams that would generate the base maps. And this has to be done for every variant. So you can imagine how expensive that is, right? Now, in the new smarter approach, what we are proposing is that you actually just run 10% of that design points in the physical dyno, and then you use that to train a physics-based model in GT speed, and use the power of high-performance computing today to calculate the rest of the points within no time. And that actually reduces the entire design, calibration cycle to 4 to 6 weeks as compared to, 2 to 6 months. And to back that up, I want to give a realistic example here from Mahindra, where they actually reduce their air path calibration. It's a task that is done for every engine at an early stage of calibration. And this takes usually about 12 weeks for them. And with the new virtual process, they were able to reduce it to 4 weeks. And with that, they could save 8 weeks of test bed time. And there are other benefits as well. They reduced their dependence on ECU suppliers. They had more control over their calibration. And of course, they took out 8 weeks from their product development time. So in summary, we did give you few examples of computer-aided strategy and smarter testing to de-risk your product development strategy for today and 5 years from now. I want to emphasize that our goal has been to keep providing solutions for now and for future technologies to be able to meet regulations, simulate extreme environments that are highly difficult to test, and of course, at the end, reduce your product development time and de-risk your strategies. With that, I would like to thank everyone for their attention and request everyone to visit our virtual booth as part of the ETAuto conference and reach out to us even offline if you have any questions. Thank you and have a great rest of the session.